in this video, we're going to be looking at the features of a parabola, and we're also going to be looking at different types of transformations. The learning intention of this video is for us to be able to identify the key features of a parabola. And lastly, we're going to be observing the impacts of different types of transformations on the most simplest quadratic equation, which is y is equal to x squared. Now, I'm going to tell you in advance that this particular video is going to be relatively lengthy because I am going to be somewhat combining the main concepts covered in two exercises, okay? So this video will be relatively long, but I'd like to tell you guys in advance that this particular video over here will be relatively long because I am going to be covering, I suppose, the main concepts and the main topics that's covered in two different types of exercises. The reason why I've decided to merge it all is because I think it makes more sense to teach them together than in separate or isolated lessons. So we'll see how we go. So the first thing I want to talk about is what is a quadratic equation. So just a reminder, guys, a quadratic is any expression or any equation where the highest power or the highest exponent is going to be 2. So if you look at the examples on the left hand side over here, these are clear examples of quadratics because in each of these examples you can clearly see, for most of them at the very least, that the power of x is always going to be 2 as the highest power. That's evident here, here, here. It's also evident for this one over here if you were to expand it, and it's also evident over here as well. In the very last example over here, it may not look like a quadratic at first, but again, if you expanded it, then this will also produce a term that has an x squared. On the examples on the right hand side over here, these are not examples of quadratics. As you can see, they don't have a power of 2 at all. Now, when you actually do happen to sketch the graph of a quadratic equation, what you're going to get is a parabola, okay? So you need to understand the differences between a quadratic versus a parabola. Quadratic just essentially means the expression or equation, whereas a parabola is this graphical form of a quadratic. And when you actually plot a parabola, you could either have a happy face or an unhappy face curve. Now, this happy and unhappy face, these aren't legitimate terms, but that's the way that I like to describe the shape of the parabolas when it's in either forms, okay? And as you can see on the right hand side over here, there are 5 main features that we're going to be looking at in today's lesson, and this includes the x-intercepts, which is also referred to as the solutions, the y-intercept, the vertex, which is also commonly referred to as the turning point, and lastly, something referred to as the axis of symmetry. However, for the purposes of just sketching the graph, you really only need to know 3 main features out of this list of 5. That's just going to be the x-intercepts, the turning point, as well as the y-intercept. So let's go into a bit more detail into each key feature of a parabola. So the very first feature that we're going to be looking at is the turning point, which is also referred to as the vertex. The turning point or the vertex can either be the highest or it could be the lowest point of the parabola, okay? As you can see on the right hand side, I've got 2 different parabolas that's displayed, one represented by the pink curve and one represented by the blue curve. And because you've got these 2 different types of shapes for the parabola, you can actually classify your turning points in 2 different types. You could either have a maximum turning point, and this is a turning point that's only found when you've got an unhappy face parabola. The reason why it's called the maximum, because for the blue graph, as you can see over here, it's the maximum because this particular point is the most highest in terms of vertically wise. It's the most highest point on the graph. In contrast, when you have a happy face parabola, the type of parabola present in these types of graphs is what we refer to as a minimum parabola. And the reason why it's referred to as the minimum is because it's the lowest position or it's the lowest coordinate found along that particular parabola over here. When you get questions related to the turning point, it's going to either ask you to identify what the turning point is, so state the turning point from the graph, or it could actually ask you to classify what the turning point is going to be. So it's asking you, is the turning point for this particular equation or for this particular graph an example of a minimum or a maximum turning point, okay? So that's what this yellow speech bubble says. The next feature that we're going to be looking at is something referred to as the axis of symmetry. Now, as you can see from the parabola shown on the right hand side, we know that a parabola is a symmetrical type of graph. And as indicated by the name, it's the axis of symmetry has something to do with the symmetry of the parabola. What the axis of symmetry is it's a vertical line that always runs down in the middle of your turning point, and in doing so, this will produce a mirror image. And when you write the equation of the axis of symmetries, it will always start off with x is equal to whatever that value is going to be. So looking at the example on the right hand side over here, these arrows represent where the position of the axis of symmetry is going to lie, and we always generally draw the axis of symmetry as a vertical dashed line, as you can see over here, and as you can also see, it always runs through your turning point. So in this case over here, if you were to write an equation for your axis of symmetry, it's just going to be whatever your x value is going to be. So in this case, because that's 1, 2, 3, the axis of symmetry for the blue parabola is going to be x is equal to 3, and for the pink parabola, that's going to be x is equal to -3. I also do want to add that when you are going to be sketching parabolas in the future, it is really critical that you are drawing your parabola as symmetrical as possible. The next key feature that I'd like to talk about is the x-intercepts. We already know that the x-intercepts is the coordinates where the parabola would cross the x-axis, and as I stated beforehand, the x-intercepts are often referred to as the solutions. As you can see on the diagram down below, the number of x-intercepts can vary. They could either have 0 x-intercepts, 1 x-intercepts, or 2 x-intercepts. And this will just depend on how high or how low your parabola is shifted along the y-axis, okay? And just to make sure that when you are graphing these, it's really critical that you need to label your x-intercepts, if x-intercepts exist, as a pair of coordinates. So that's what I've done over here for these examples. I'd also like to add that the axis of symmetry is also found halfway between the x-intercepts. And this is very useful when you've got a graph and you know what your x-intercepts are, but you don't really know the position of your turning point because it's not really indicated to you at all. So what you need to do is pretty much find the average of your two x-intercepts values, so add them together, divide by 2, and this will give you what the axis of symmetry is going to be. In terms of finding what our x-intercept values are going to be, this is going to vary depending on how our equation is actually expressed. So normally when we're trying to solve for the x-intercepts, we're going to sub in y is equal to 0. But as I said, depending on how the equation would look like, there are many different types of methods that we could actually undertake. One of the methods involves using inverse operations and then just transposing the equation to solve for x. So that's one way we could do this. Another way we could do this is by factorizing, so putting everything into a set of brackets and then applying the null factor law, and we'll look into that in future lessons. Another way we could do this is also by using something referred to as the quadratic formula. So we just substitute values into the formula and it will automatically spit out what the x-intercept are going to be. And as I said, we're going to also look into this in a bit more detail in future lessons. And lastly, the last key feature we're going to be looking at is the y-intercept. And as you guys are already aware, the y-intercept is the coordinate where the parabola crosses the y-axis. I'd like to emphasize again that when a question asks you to sketch the graph, make sure you are labeling your y-intercepts as a pair of coordinates, okay? So this is how you should be representing this graphically. If you're trying to find out what the y-intercept value is going to be, what you would do is you would need to substitute x is equal to 0 and then just simplify to solve for y. So let's say that this is the equation for the graph shown on the left hand side. If I was trying to show or prove that the y-intercept is 3, which is illustrated there, what I'll do is I'll sub x is equal to 0, and if I do that, I'll therefore just start to simplify things down. 0 minus 0 plus 3 is going to give you 3, hence 3 is your y-intercept. And as I said, it's always encouraged to write this as a set of coordinates. Now that we've gone through all the features of a parabola, let's now do an example together that goes through all of the key features. So the first part of the question wants to identify what type of turning point is present on the graph shown on the right hand side. And since you've got a happy face parabola, the type of turning point that's present is going to be a minimum, because as you can see here, that's the lowest point found on the graph. So this is going to be a minimum. The second part wants you to state what your y-intercept value is going to be, and make sure you're always representing this in a coordinate form. So in this case, your y-intercept is going to be 0, -2. Similarly, you do the same thing for your x-intercept. So your x-intercept is going to be -1, 0 and 2, 0. And for the very last question, it wants you to write down the equation for the axis of symmetry. And remember that the axis of symmetry can be found either by finding out what is the x value of a turning point, because it always cuts through the turning point, or alternatively what you could do is you could take the average of your two x-intercepts, and that will also give you the value for the axis of symmetry. In this case over here, I could readily eyeball that your axis of symmetry is occurs halfway between 0 and 1. So in this case over here, your axis of symmetry is going to be x is equal to 0.5. Now that we've gone through an example, have a go with answering this question. Give yourself 1 minute and we'll compare our answers together. If you guys have done this correctly, for this particular graph over here, you're going to have a maximum turning point because that's the highest value. The coordinates of a turning point in this case over here is going to be 2, 4. The y-intercept value is going to be the origin, which is 0, 0. Your x-intercept for this particular parabola is going to be 0, 0, so at the origin, as well as 4, 0. And lastly, your axis of symmetry always cuts through the middle of your turning points. Hence, it's going to be when x is equal to 2. Before I show you the different types of transformations, you guys actually need to have an understanding that there are different ways that a quadratic equation can be expressed. So quadratic equations can be represented in a number of forms. One of the forms that it can be represented in is something referred to as the standard form, also referred to as the polynomial form. And when it's expressed in this particular form, it's in the form of y is equal to ax squared plus bx plus c, where the letters a, b, and c, the ones that I've color-coded, can represent any number. Another way of representing a quadratic equation is by representing it in the turning point form, also referred to as the vertex form. And as given by its name, the main advantage when it's represented in this form is that it readily tells us what your turning point is going to be, and we'll look into that in further detail in the next lesson. And another way that you could also represent a quadratic equation is in the factorized form, also referred to as the intercept form. And the great advantage about this form is that it actually readily tells you what your x-intercepts are going to be. So based on this structure, you should be able to recognize the advantages and the different forms a quadratic equation can be represented in. Now that you know that, let's now look at what quadratic transformations are. So a transformation is where you can change the position, change the size, or change the shape of the actual parabola. And there are three main types of transformations that you need to be aware of. The first one is referred to as a translation. So a translation, or when you're translating, this means that you're actually moving or you're shifting the parabola either horizontally or vertically along the Cartesian plane. The next type of transformation is something referred to as dilation. And when you're dilating, this means that you're going to be changing the size of the parabola. And lastly, the next transformation is referred to as reflection, and as you might be aware by its name, this involves flipping the actual parabola from a happy face to an unhappy face parabola, or vice versa. Before we move on, it is really important that you guys understand the definitions of these three different types of transformations, as I will be asking you guys questions later on what type of transformation has taken place. Now, the reason why I've shown you guys the different forms of a quadratic equation that can be expressed in is because the different letters found in different forms actually contribute and change the actual shape or size of the actual parabola. So what we're going to be doing from this point onwards is we're going to be examining how does the value of A, B, C, H, and K that's found in the standard and turning point form changes the actual equation itself. So what I'm going to get you to do is I don't actually recommend you to be copying down any notes from this point onwards. Just wait until you reach the summary page, which will therefore show all the different types of transformations in a greater detail. Now, to help you understand the 3 different types of transformations, I'm going to now play a video, and what I want you to do is I want you to comment, how does adjusting the value of A, okay, in the standard form affect either the shape of it, affect either the size of the parabola, or how does it affect the position of the parabola, okay? So as you can see here, again, I've got the standard formula of a quadratic expression, and I'm just leaving the value of B and C equal to 0. And that shows you over here. All I'm simply doing is adjusting the values A. So I will now play the video, and I want you to comment on the Edpuzzle, how does it actually affect y is equal to x squared in this case over here. So I'm now adjusting it, and I want you guys to comment, how does it affect the y equal to x squared. Now, as you can see over here, you probably would have noticed that in this case, if I was increasing the value of A, what you would have realized is that this resulted in a very thin parabola, okay? Conversely, when I was actually decreasing my value of A, in this case over here, what I produced was a very thick or a very wide parabola. So this type of transformation is referred to as a dilation. So dilation involves changing the size of the parabola, okay? So as we said, the value of A in this case makes the parabola either thinner or thicker. We said that any values that are greater than 1 or any large A values, this will result in a very thin parabola. So in this case of here, if you look on the diagram on the right hand side, the parabola that has the gray curve, that's your y is equal to x squared. So that's your parent function over here. Now notice in this case over here, the blue graph, that's where you've got a value that's bigger than 1. Okay, so a large A value, and as you can see over here, this has resulted in a much more thinner parabola. Conversely, or in contrast, when you've got an A value that's smaller than 1, then this is going to produce a very wide parabola. And I need you guys to actually understand this. So in this case, if you've got a quarter, then you're going to get a much wider, a much more thicker parabola. Now, in the video before, what I was showing you is what would happen to the value of A when it's in the standard form. So when it was in the y is equal to ax squared plus bx plus c. But if you were to change the value of A in the turning point form, what you would see that this also happens in the exact same way as well. So in this case here, I've got this particular equation in the turning point form. So if, just to recall, the turning point form was y is equal to a bracket x minus h whole squared plus k, okay? So in this case of here, if you were to adjust the value of A, I'm going to play the video right now. You can see that a big A value makes the graph thin, but when I start to decrease my A value, I'm going to therefore produce a much more wider parabola over here, okay? Now, I'm now going to be looking at a different type of transformation. So I'm going to see what is the effect of changing the value of C when it's represented in the standard form. So again, I want you to comment what will happen to the y is equal to, so this is in the y is equal to x squared, what happens to this particular parabola over here. So in this case over here, I'm now increasing my value of C. So tell me what happens to the parabola. All right, guys, if you've answered this successfully, what you would have realized is that when I was actually increasing my value of C, this would have caused my parabola to shift up along the vertical axis. But when I had a negative C value in this case over here, what this did was that this actually moved the parabola down along the y-axis. So this type of transformation is referred to as a translation. So translation just means to move or means to shift the parabola. So when you're expressing the quadratic equation in the standard form, the value of C represents how much did it move up or down along the y-axis, and it also corresponds to the y-intercept. So in the orange equation over here, that's your basic y is equal to x squared. Now notice that for the green one over here, your value of C is equal to a positive 2, so therefore that means you're shifting up your turning point 2 units up. So now your turning point is going to now be 0, 2, and that was also going to be equal to your y-intercept. Similarly, for this one example over here, I've got a C value of negative 2, so therefore you're moving 2 units down in this case over here. This also applies when it's in the turning point form, but we don't use the letter C in this case in the general form. We use the letter K. Now note that the letter K, so any number that's found outside of the brackets over here, this is going to tell you how much is either moved up or down in this case. So I'll play the video just to show you, but if I had a positive K value, then this means that I'm moving my parabola up. So in this case over here, I'm going to drag the parabola up, but if I actually decrease it, then it will go down. So that's one thing that I want you to note down from this particular slide. All right, so now what we're going to investigate is what would happen if you actually change the value of B in the standard form. Okay, so now I'm going to play the video. In this case, if you notice that when you're changing the value of B, what's actually happening is that you're kind of dilating, you are somewhat changing the size of the parabola, but you don't actually need to know this too much at all, because change the value of B doesn't really I suppose enhance our knowledge in any way. But for the value of A as well as the value of C, you really need to know how that actually impacts the size, the shape, the position of the actual parabola. Okay, so nobody cares, you don't need to know this at all. Now in this case, this is very important, but what would happen when A is a negative number? So I'm going to play the video and I want you to comment what actually happens to the actual graph. So in this case over here, I'm now changing the A value to a negative number. Now, what you would realize is that by changing the value of A to a negative value, what this would have done is that you would have reflected, or you would have flipped the actual parabola over, okay? So in this case, when A is negative in both the standard form as well as the turning point form, you are going to have an unhappy face parabola, okay? And in this video over here down below, I'm going to show you in this case in the turning point form what happens when you change the value of A to a negative. So in this case, when I'm playing the video, when I've got a positive A value, you've got a happy face, but when my A value is negative, I'm going to have an unhappy face parabola, okay? Now, the very last type of transformation that we haven't looked at yet is translating horizontally. So translating horizontally means just to shift the curve either left or right along the x-axis. Now, I want to emphasize that horizontal translation is only really obvious if the equation is represented in the turning point form. It's going to be a bit more harder for you actually to identify whether it's actually moved left or right when it's presented in the standard form. So for now, I just want you to know that in the turning point form, you could easily tell. And in this case over here, for you to tell whether something has translated horizontally, if it's represented in the turning point form, you just need to look at the value of h. So h is pretty much any number that's found inside of the bracket within the turning point form. And this will tell you how many units it moved left, how many units it moved right. In this case over here, when you've got a h value that is greater than 0, so you've got a positive value over here, you're going to be moving the graph to the right. However, when you've got a h value that is less than 0, you're going to be moving the graph to the left. Now, this is where it will get a bit confusing because you've got a subtraction sign over here, okay? So in this case over here, many people often think it's opposite. So I'll show you what I mean by this. So I'm going to play the video right now. And what I want to show you first is what would happen when I increase the h value, okay? So in this case over here, when I increase the h value, notice that I am going to be moving to the right, as I said over here. However, when I decrease my h value, so when I've got a negative h value over here, notice that in this case over here, I'm moving to the left. Now, if I pause the video at this moment over here, let's say that this is my equation. So fx just means y in this case. Y is equal to 1 bracket x minus negative 1.4 squared. Now, we don't ever write it like this when I give you an equation. It's often represented like this. Instead, y is equal to 1 bracket x plus 1.4 whole square, okay? Because we know that two negatives make a positive. Now, even though that if I simplify it and I leave it as a positive here, many students think that, okay, my h value is positive 1.4, so therefore it moves to the right. But as you can clearly see here, you're not moving to the right at all. You've actually moved to the left 1.4 because you actually have a negative sign over here. So you have to take that into account. And so therefore, many people often think that it's always going to be the opposite. That's one way to actually remember this. So just to quickly summarize all the different types of transformations that we've covered over here, if you're a person that likes simple notes, then this is probably going to be the best notes for you. In this case over here, I said that when you change the value of A, what's happening is that you're going to be either dilating it. So in this case, if you've got a big A value, you're going to have a narrow graph. when you've got a small a value, you're going to have a wider graph. When your a value is negative, then you're going to reflect it. You're going to have an unhappy face parabola. For b over here, you're also dilating, but it's not really important, so don't need to really be concerned about that. But when you change the value of c, what you're doing is you're shifting the parabola up or down, and c also corresponds to your y-intercept as well. Now, when it's in the turning point form, so in this particular form over here, similarly, a is going to tell you how much it has been dilated or reflected. But what is different in the turning point form is that this number over here that's found within the bracket, so h, this will tell you the number of units is moved horizontally along the x-axis, okay? So I often say to my students that just think of it as opposites. So if the equation was y is equal to x minus 1 whole squared, this -1 means it's moved one direction positive, so it's moving one unit to the right, okay? Whereas if it was y is equal to x plus 1, okay, plus 1, think of its opposite, you're moving to the left instead. And k, in this case over here, if the number is found outside of the brackets, then this will tell you how much has it actually moved vertically up or down, okay? And there is no opposites for that. So if this, in this case over here, if I added +5, then that means you're moving 5 units up. If I said -5, you're moving 5 units down. But if you're a person that needs more detailed notes, then this is something that might be useful for you instead. So this pretty much just summarizes all the different types of transformations for both the standard form as well as the turning point form. So please copy this into your notes, whatever notes is more better for you guys. We're now going to be assessing your understanding. So I want you to give yourself 1 minute, look at your notes and tell me what type of transformation do you see in this graph over here. Is it an example of a horizontal translation, vertical translation, reflection, or dilation? If you guys have answered this correctly, you would have seen that because I'm changing the value of my C in this case over here, this is an example of a vertical translation. For my next question over here, in this case, I am changing the value of A. And notice that when I'm changing the value of A, I'm pretty much going to be dilating in this case over here. So I'm changing the size of it. And in this example over here, I am changing the I suppose the symbol in front of A. So I'm changing it from positive to negative. In this case over here, this is an example of a reflection. I'm going to go through one more example over here before I pretty much end today's video. So in this question over here, this question from exercise 7a wants you to copy and complete the table for the following graphs. So for part A, you need to identify whether the turning point is classified as a minimum or maximum. In this case over here, 4x squared is going to be a minimum. Is it reflected in the x-axis? So do you have an unhappy face parabola? No, you don't. So there's no reflection present. You have to state the coordinates of your turning point. So in this case, this is your turning point here. So that's going to be at 0, 0 at the origin. For this particular column over here, it wants you to solve by substituting x is equal to 1. So what's the y value when you sub x is equal to 1? So in this case over here, it will be 4, 1 whole squared. 1 squared is equal to 1. 1 times 4 is equal to 4. Now, is this particular graph y is equal to 4x squared more wider or narrow as opposed to y is equal to x squared? In this case over here, you can see that's because a is a big number, it's going to be more narrower. For part B, in this case over here, you would also see that this is an example of a minimum. Is there any reflections present? Do you have an unhappy face? No, you don't. So there's no reflection present. In this case over here, remember, this is in the turning point form. It kind of looks like a turning point form. So your turning point is going to be the opposite value over here, which is -2, as you can see here. So it's going to be -2, 0. Your y value, so substitute x is equal to 1, so therefore y is equal to 1 plus 2 whole squared. 1 plus 2 is 3, 3 squared is 9. And in this case over here, because I've got no number in front of the bracket, in this case, it's going to stay the same. A is equal to 1, so you haven't really made it more narrow, or you didn't actually stretch it out. You didn't make it more wider. And for my last example, is it a maximum minimum? In this case over here, because I've got an unhappy, it's an example of a maximum turning point. There is a reflection present, and the turning point in this case over here is going to be 0, positive 3. Substitute 1 in, so therefore what is 1 squared? That's equal to 1. Put the negative sign in front, so that's going to be -1. -1 plus 3 is equal to positive 2. And in this case over here, because the coefficient in front of x squared is equal to 1, this is also going to remain the same. So what I want you to do, now is I want you to now answer these questions over here. Give yourself 5 minutes and then compare your answers with my answers. If you guys have done this successfully, then these are the answers that you should have obtained. So I'm pretty confident that you will get all of these answers correct. And in terms of the textbook questions, there are a lot of textbook questions that I'm going to be asking you to do. So I want you to answer questions 1, 2, 3, 4, 5, 6, 7, 8, as well as question 13. For all of these questions over here, do not copy down or draw down the actual graphs. That's just going to be way too time consuming. All you really need to do in your exercise book is pretty much copy down the table and then answer it as it is. So do that for questions 2, 3, as well as question 4 over here as well. Now for questions 5, 6, 7, now although I've given you this table over here, that wasn't actually present, but in order to answer it, I think it's best if you actually produce a table format like this and have the number of rows that corresponds to the number of questions you found in question 5, so all the way up to L in this case. Hopefully you're able to address all of these success criteria. Thank you for watching today's video. I'll see you guys again in the next video. Bye.